The title of this video is Electromagnetism throughout history. Electromagnetic phenomena were already known at the time of the ancient Greek. In fact, tales of Miletus perform probably the very first important experiment with electric phenomena. He took a piece of amber he rubbed it with a cloth, let's say in this region. Then he took a little piece of paper and he was able to lift up a little piece of paper with this object made of amber, which was previously rubbed. What is striking about this experiment is that the little piece of paper would like to fall to the ground because of the gravity due to the entire planet Earth. However, the electric energy, the electric force, due to this simple small piece of amber, is capable of overcoming the gravitational force due to the entire planet Earth. This clearly shows that the electric force is a very important force. In fact, it's one of the fundamental forces in nature, and we really want to understand what it's all about. What I'm about to say, of course, Tales of Miletus was not able to do at this time. This is something which we only now know. Now we know that if we take a hydrogen atom, so we know that roughly it comprises a nucleus made of a proton plus, around which somehow an electron minus circulates, moves around in a sort of orbit, in a very simplistic, cartoonish kind of representation of the hydrogen atom. As it turns out, the interactive force, which I sketch with this type of double arrow, the interaction between the nucleus and the electron, the proton and the electron, in this case, is about 36 orders of magnitude larger than gravitation, than gravitational forces. Once again, this clearly tells us that electromagnetic phenomena are really, really important, and we need to understand them carefully. Unfortunately, for many centuries, electromagnetic phenomena were not investigated and kind of forgotten until the 16th century, when for the first time, scientists were able to distinguish between electric and magnetic phenomena. In the 17th century, another very important experiment was made for the first time. So people repeated what Tales of Miletus did with amber many centuries before, but this time, not only they made experiments with amber, but also with glass. And so what people did, they took both a piece of amber as well as a little piece of glass, they rubbed both of them, performing the same operation, a similar operation as Tales of Miletus did centuries before. And now what they notice is that Interestingly, when a powder of medium, and note that medium is red, has a red color, so when a powder of medium was released around the amber, this powder was attracted by the amber. On the contrary, it was repulsed by the glass. At the same time, they took a powder of sulfur, which is yellowish. In this case, they noticed that the sulfur was attracted by the glass. And repulsed by the amber. With this very simple experiment, we can distinguish, people were able to distinguish between two different types of electric properties, different type of properties of electricity. So one we can call it red, a red property, and the other one we can call it a yellow property. As it turns out, what is happening here is that this rubbing procedure generates charge. And as I told you in the video named the Electromagnetism project, charge is one of the sources, is the source in nature of the electric field and therefore of the electric potential. And so here what people were able to do with these two different experiments is to distinguish between a red charge and a yellow charge. And in fact, we could still call it like this if we wanted to, but as we then are going to learn in one of the upcoming videos, red and yellow actually mean effectively positive and negative. So red is in fact negative, so amber is negatively charged, whereas yellow is positive. So glass is positively charged. Okay, now linking back this red negative discovery of amber to the amber we discussed in the beginning, we also understand the etymology of the word electron. So the word electron is from Greek, and it means amber. So it's quite easy to remember that amber charges negatively because its own name means electron, which is a negative particle, as we know now. Whereas glass, for example, charges positively. So positive and negative charges. And again, in one of the next videos, we are going to go into the detail of a detailed discussion of charge, which, one more time, it's one of the sources of the electromagnetic force, in particular, the source of the electric field. In the 18th century, a major breakthrough happened. Charles Augustin de Coulomb, a French physicist, I guess didn't really care about La Guillotine and all the beheading which were happening down the street from his lab. And during those days of the French Revolution, he was able to perform a very important experiment which eventually allowed him to discover a law which goes under his name, Coulomb's law. Before even attempting to delve into the structure of Coulomb's law, which will be the topic of another video coming up soon, it's worth pointing out what is the meaning of law in physics. So law in physics is conceptually similar to axioms to an axiom in math. In the case of a physics law, the procedure that us scientists need to follow in order to discover a law is to perform a myriad of experiments. That is a vast amount of experiments. So a very large number of experiments. Okay, the more you do, the better it is. In fact, in principle, you should do infinite experiments. From this empirical evidence, so a law in physics is purely empirical, from this empirical evidence, we are able eventually to deduce a law, and that's what Coulomb did in his experiments. So we are able to find a law which, as long as all experiments point in the same direction of the same law, we use it to eventually prove theorems and use it to solve problems in physics. So it's very similar to the axioms in math. Now, so this one, we need empirical evidence. Which eventually gives us a law, which is what finally we use. Perhaps some theorists may tell you that it is possible to postulate in a sort of axiomatic fashion the entire physics. However, I personally believe that without a strong empiric knowledge of the matter we are treating, in this case the electromagnetic phenomena, it's impossible to really be sure and that what we are studying is correct. So I really think, in my opinion, and this is the procedure we're going to follow in this course, we will start always from, well, at least in the discussion of the electric field, we will start from the laws of physics, which are again empirical laws that people, scientists, made experiments and were able to show that they are true, they are correct. So we'll use these laws. From this, we will eventually prove theorems, and eventually we can use these theorems to solve problems. But all these theorems still stem from laws which have an empirical origin. Okay, so to give you a flavor of what we're going to do in this course, we will start from Coulomb's law. So we will begin with Coulomb's law, and from this law, we will show a theorem, which is Gauss's theorem. Which encodes the same information as Coulomb's law, but in a different fashion. So that's the spirit here, okay? And so from these basic laws, we will eventually be able to find a set of equations, which are called Maxwell's equations. So EQS with a dot, it's an abbreviation for equations, which we can use to solve problems. But these Maxwell's equations, in the case of the electric field, encode pretty much the same information as Coulomb's law, with some caveats, and I will come back to that soon in an upcoming video. All right, so now that we know a little bit what a law is, I have a question for you. And the question I have for you is, do you know Coulomb's law? Do you already know it? If not, do you know something similar? Do you know a similar law? I'm sure you do. And so I urge you to follow this procedure, to think about these questions, which I will keep highlighting in yellow throughout these videos. And every time you see one of these yellow boxes, and on the bottom right corner, I write Piazza, I want that you start to discuss about these yellow boxes in Piazza with your fellow students. And eventually, when I will tune into Piazza to see what's going on, perhaps I may chime in when I see fit to interject and discuss about these topics which I'm highlighting in yellow. But I really want that you start a discussion among yourselves about all these topics. And so let's start with this. So do you already know Coulomb's law? Feel free to answer in Piazza if you already know it. Do you know a similar law? I'm sure you do. So let's start a discussion there. And in fact, I would also add, if you know a similar law, what are the differences between this similar law, which is a very important law in physics, and Coulomb's law? So think a little bit, meditate about this, and try attempt to answer these questions in Piazza, please. And for more discussions about Piazza and the other tools we are using in this course, please refer to another video where I explain all the rules of the course. All right, we will come back to Coulomb's law soon in this course. Instead, let me quickly touch on another couple of topics which were developed in the 18th, 19th century. All right, so let's continue with our history of electromagnetism. In the 18th century, besides Coulomb's law, which we will discuss in very much detail in a number of videos coming up, people were also able to categorize materials into different types. And so these two types of materials behave differently when exposed to the electromagnetic force. What are these two types of materials? These are insulators and conductors. So people noticed that, for example, if we take a piece of copper, let's say a parallelepiped, a small parallelepiped of copper, and let's say we rub it using the very same procedure as tiles of Miletus did with a piece of amber, well, in principle, you should be able to lift up a small piece of paper. However, if we touch this piece of copper with our hand, typically this does not work. And why is that? We'll come back to this in a minute. The other thing people notice is that if instead of touching the parallelepiped of copper directly with our hand, we incorporate a handle to this piece of copper, so we have the same situation here with a little parallelepiped of copper. However, this time we attach a handle let's say made from amber or glass. Let's say glass in this case. And we touch, instead of the copper itself, the handle made of glass with our hand. Then, by rubbing the copper, then we are able all the time to pick up a little piece of paper. You can try to do this kind of experiments yourself. I try to do here with these markers and try to rub them. Unfortunately, it depends a lot on the ambient humidity and all that, and so it's kind of not always works, but you can try. It's a pretty simple experiment. So this actually pointing in the following direction. It seems that somehow when we touch this piece of copper with our hand, somehow the charge which we create by means of this rubbing procedure does not remain on the copper itself. And so by means of this simple type of experiments, people were able to distinguish between these two different types of materials, those that can keep the charge and those that they don't keep the charge, where the charge moves. Okay, so it's free to move. And so these two categories again are called insulators here on the left hand side, and conductors on the right hand side. As it turns out, copper is a conductor where the charge, once created, can move freely, and so not always we can keep it where we want it to keep it. Whereas in the case of glass or amber, let's say glass can keep the charge fixed. And so the key word here is that in the case of glass, the charge, we have a fixed charge. In the case of copper, we have so-called free charge. The charge is free to move. That is very interesting. So this also seems to show that maybe our body is also conductive. Is that true? Well, this is a simple multimeter which allows us to measure, in this case, two of the three circuit elements we discussed in the video called the Electromagnetism project. One is resistance. And so in the case of resistance, let's see what happens when I touch these two terminals with my own body. Well, we see something like a few hundred kiloohms. So interestingly enough, our body is conductive. So it's similar to copper. It's more similar to copper than to glass, as it turns out. Here I see about 500 kiloohms. That's a pretty good resistor. Actually, it's not only conductive, it's also a little bit capacitive. So this same instrument allows me to measure relative capacitance. And if I were to measure that, again, touching this with my body, I see about 5 nanofarad. Now, unfortunately, this simple multimeter is not capable of measuring inductance, which is the third circuit element we are going to discuss in this course. But actually, our body is also inductive. And in fact, we can use our body as an antenna to capture signals from an AM radio, which is sort of what I was doing in the first video you've seen in this course. So our body, if you want, belongs to this category of conductors. But again, the interesting thing is that our body is characterized by resistance, but also by capacitance and by an inductance. Okay, but somehow charge is free to move through our body. Now, a question which I leave here for you to discuss in Piazza is, can you list more both insulators and conductors? Please discuss about that in Piazza. All right. Now, perhaps it's worth already now at this stage in the course having a sort of microscopic look at insulators versus conductors. And we will come back to this very much in detail later in the course. In 242, we will discuss in detail, a bit more in detail, how conductors work. And in 342, how insulators as well as magnetic materials, which are similar to insulators but for the magnetic field, work. So in the case of conductors, if you take a piece of copper, inside this conductor there is a lattice, in fact a periodic lattice, where at each vertex of this lattice we have positive charges. There's the positive in green and negative, actually positive we've done it in yellow because it was sulfur, and in red, medium, we do the negative charges. So at each vertex here, we have a positive charge, etc. I will not sketch all of them. So these positive charges, which are called ions, they are fixed in this periodic lattice, in this periodic structure. Whereas electrons, these negative particles, are free to move within this lattice, and eventually they can collide with the ions, or they can even collide with other electrons, and therefore scattering. We'll discuss about this later. So microscopically, in a conductor, we have negative charges which are free to move. So the electrons are free to move. See, as I said here, the charge is free to move in this case. Same in our body. In the case of insulators, and again, this we will discuss about this extensively in 242. The case of insulator, we will discuss about that in 342, but in a few words, the way it works in this case is that we have an object, let's say a piece of glass, or well, I'm not going to tell you another type of object because I want you to think about it. It's one of the questions here in Piazza. So in this case, in the case of an insulator, inside the insulator we have molecules, and these molecules are made, for example, of a pair of positive and negative charges. So we can have a few positive charges. Let's do 3 of them, for example, here, which are attached to negative charges in this fashion. So they're all attached to each other like this. Okay. And so these molecules form what is called a dipole, an electric dipole. Okay. So we'll come back to this in detail in these two courses, 242 and 342. So these are electric dipoles. As it turns out, these charges are pretty much fixed with respect to a center of charge, which you can think of as a center of mass, if you want, between these two particles. They are pretty much fixed around that center of charge. Okay, so they're fixed there. We can only shift them around very little, for very little amounts. Okay, so in this case, these charges are fixed, and so they don't move. Okay, so that's the key word, fixed, and that's why these materials behave as insulator. And really understanding conductors, microscopically, conductors and insulators, it's critical to solve problems when we expose this type of materials to the electromagnetic field. Okay? All right. So to summarize what happened here, in the case of conductors, the charge can move macroscopically around the object by finite amounts, whereas in the case of insulators, it can only move a very little amount, so microscopically. So in one case, the charge is free. In the other case, the charge is fixed. This is a very important categorization for materials in electromagnetism. So now, it's perhaps worth giving an important definition, which is that of uncharged objects. So what is an uncharged object? An uncharged object, which is also an object said to be in the neutral state, so an uncharged object is an object where the number of positive charges and the number of negative charges is the same. Let's say 3 positive equal to 3 negative. Okay, with this definition in mind, let's describe another experiment which was done in the 18th century. So the experiment is as follows. We have, in fact, a ceiling, like this one, where we hang through a little wire, very light, a very light piece of wood. We wrap this piece of wood with aluminum foil. At this time in this experiment, so time t equals 0, so this is the beginning of the experiment, at time t equals 0, we assume that at infinite distance, so infinitely far away from this pendulum, if you want, we have, let's say, a piece of glass which has been previously rubbed to create an excessive charge on this glass. So to charge it, in this case, we know that the glass will charge with a positive charge, let's say with 3 positive charges. Okay, that means this rubbing, we charge it. So the glass is charged, but it's infinitely far from this pendulum, which in fact is called the electric pendulum. Okay, so it's infinitely far, so they don't interact with each other because it's very far. So what happens when at time larger than 0, we bring this glass, which is previously charged with positive charge, from an infinite distance to a finite distance, where in this case, this is our ceiling here. As it turns out, this is what happens, something quite remarkable. the pendulum moves. So this is the wood, this is the aluminum foil, and what happens here is that when the glass is in close proximity to the pendulum, these positive charges somehow make the pendulum move and be attracted to the glass. So it moves away from this equilibrium position in which it was by an angle theta at the time t, let's say larger than 0, whatever time that is. Okay? Why is that? The reason behind this is because the free charges which are on the aluminum foil, which is another type of conductor similar to copper, you could put a copper foil, it's the same thing. The free charges somehow interact with these positive charges, they are attracted or repulsed by these positive charges. So here I have a question for you which I want you to discuss again in Piazza. So suppose they give you two positive charges. These two positive charges will interact. Sorry, of course they interact. Will they attract to each other or repulse to each other? This is the question. Let me box it as always for our Piazza discussions. Okay, will they interact? Will they be attracted or repulsive from each other? So if you understand, if you know how to answer that question, well, as it turns out, these positive charges on the glass, what they do, they displace free charge on the aluminum foil in such a way that negative charges will be moved in proximity of the glass, in this case 3, because I put 3 positive charges, so I need to have 3 as well, and an equal number of positive charges will be displaced, moved away in the other direction on the aluminum foil. Okay. Note that the amount of positive charges and that of negative charges is the same, which means the aluminum foil remains always uncharged throughout this experiment. It's always uncharged, okay? So in this case, the fact that the aluminum foil contains charges which can freely move makes this effect possible. So the 3 positive charges on the glass, they do not move, they are fixed, whereas those in the aluminum can move and they displace in this fashion. Okay, we'll come back to this in detail later on in the course. This phenomenon is called electrostatic induction. Very important, okay? Now one last question that I have for you is, what happens when eventually I move again? Let me do this question in yellow. So what happens when I move back to infinity my glass? Discuss about this. Think and meditate about that. What happens? In particular, what happens to the pendulum itself? What happens to the charges on the pendulum? Okay? Is this uncharged charge at the end of this experiment? Think about that. Okay? All right, so this was an important experiment done again in the 18th century. The 19th century eventually became probably the most important century for electromagnetism, and a number of breakthroughs happened in that century. So from Gauss's theorem to Faraday's law, eventually Maxwell managed to put together all these laws and to make a complete theory of electromagnetic phenomena. Then eventually Hertz was able to use all this theory to make important experiments to show electromagnetic wave, and without electromagnetic wave you wouldn't be able to use your phone or your Wi-Fi. And then in the 20th century, even more, people were able to, for example, invent the transistor, which is all based on electromagnetic phenomena. And without the transistor, all the computers we are using now wouldn't work. So obviously this clearly shows that understanding deeply the electromagnetic phenomena is crucial if you want to understand all the technology we are using right now in this space around us. Bang!